What is the Terraform plugin SDK?
The Terraform plugin SDK is the older Go library for building Terraform providers. It provides the interface between provider business logic and the Terraform plugin protocol, handling gRPC communication, schema definition, CRUD operations, and state management. The SDK uses a helper/schema package where resource schemas are defined using a map of schema structs with type, required, optional, computed, and validation fields. While still supported, new providers are encouraged to use the Terraform plugin framework instead, which provides a more idiomatic and type-safe Go experience.
What is the Terraform plugin framework?
The Terraform plugin framework is the modern Go library for building Terraform providers, offering significant improvements over the SDK. It uses Go generics and a strong type system to provide type-safe schema definitions, plan modifiers, and validators. Resources and data sources are implemented as Go structs that satisfy defined interfaces. The framework encourages separating provider logic from the Terraform protocol concerns. It supports advanced features like deferred actions, write-only attributes, provider-defined functions, and ephemeral resources that are not available in the older SDK.
How do you build a custom Terraform provider?
Building a custom Terraform provider involves creating a Go module that implements the provider interface from the plugin framework, or SDK. You define the provider schema, authentication, and endpoint configuration. Then implement resource and data source types with their schemas, CRUD methods, and import logic. The provider binary communicates with Terraform core via a gRPC protocol over a Unix socket. For development, you configure a development override in ~. Terraform RC to use a locally compiled binary instead of a registry version. Provider acceptance tests use the testing framework to create real resources against an actual API endpoint.
What is the gRPC-based provider protocol in Terraform?
Terraform providers communicate with Terraform core using the gRPC provider protocol, defined in protocol buffers. When Terraform init runs, it downloads provider binaries. When Terraform needs to interact with a provider, it spawns the binary as a subprocess and communicates over a local Unix domain socket using the Proto6 or Proto5 protocol. The provider implements RPC-TKS for get provider schema, configure, read resource, plan resource change, apply resource change, import resource state, and others. The plugin framework and SDK abstract these protocol details, so provider developers work with high-level Go interfaces.
What is the difference between required, optional, and computed attributes in a provider schema?
Required attributes must be specified in the Terraform configuration by the user. The provider will error if they are absent. Optional attributes can be omitted from configuration and will be null or use a provider set default. Computed attributes are set by the provider during apply and cannot be set by the user. They are known only after the resource is created. For example, the ID assigned by the API. An attribute can be both optional and computed, meaning the user can specify a value, but the provider will set it if omitted, which is common for auto-generated names and computed defaults.
What are plan modifiers in the Terraform plugin framework?
Plan modifiers are functions that run during the planning phase to adjust the plan value of an attribute or signal that a resource must be replaced. They are attached to schema attributes and allow providers to implement behaviors like requiring replacement when an immutable attribute changes, using a prior state value when the configured value is unknown, or nullifying computed attributes when a triggering attribute changes. Common built-in plan modifiers include requires replace, useState for unknown, and requires replace if configured. Custom plan modifiers implement the plan modifier interface.
What is customized diff in the Terraform plugin SDK?
Customize diff is a function in the Terraform plugin SDK that runs during the planning phase and allows providers to customize the diff between current and proposed resource state before it is presented to the user. It enables complex conditional replacement logic, computing attribute values based on other planned values, and writing more expressive error messages. Customized diff functions receive the current state and planned configuration and can call helper methods to force new resource creation or set attributes. In the plugin framework, this functionality is implemented through plan modifiers attached to individual schema attributes.
What is state upgraders in a Terraform provider?
State upgraders are functions in Terraform providers that migrate existing state from an older schema version to the current schema version. When a provider changes its resource schema in a breaking way, renaming attributes, changing types, or restructuring nested blocks, an existing state uses the old schema. The provider includes a state upgrader that transforms old state to the new format. Terraform checks the schema version stored in state against the provider's current version and runs any applicable upgraders sequentially before using the state. This enables non-breaking provider upgrades even when schema changes are necessary.
What is import state in Terraform providers?
Import state is the provider-side implementation of the Terraform import command. When a user runs Terraform import, the provider's import state method receives the resource ID string and returns one or more resource instances with their state populated from the actual infrastructure. After importing, Terraform reads the full resource state by calling readState, filling in all computed attributes. Provider authors implement import state to define how a resource ID is parsed and translated into a full resource state. Resources without import state support cannot be imported and must be created or managed through other means.
What are acceptance tests in Terraform provider development?
Acceptance tests in Terraform provider development create real infrastructure resources against an actual IP endpoint, not a mock, to verify that provider CRUD operations work correctly. They are written using the resource/test framework from the plugin SDK or framework and run as Go tests. Each test case specifies a configuration, checks that the resulting state has expected values, performs update operations, and verifies that destroy removes the resource. Acceptance tests are gated by an environment variable like tfacc equals 1 to prevent accidental execution, and typically run against real cloud accounts in CI.
What is the Terraform core architecture?
Terraform core is a Go binary that implements the language runtime, configuration loader, expression evaluator, state manager, graph walker, and provider protocol client. The core's main execution phases are configuration loading and evaluation, graph construction using resource dependencies, plan computation by comparing desired state against current state, and graph-based applied traversal. Providers are separate binaries spawned as subprocesses. The core communicates with backends for state storage and locking. The architecture is intentionally modular, all resource-specific logic lives in providers, keeping the core independent of any specific infrastructure technology.
What are the execution phases in a Terraform apply?
A Terraform apply execution proceeds through several phases. Input phase reads and validates configuration and variables. Initialization ensures providers are ready and state is accessible. Refresh phase reads current resource state from providers to detect drift. Planning phase builds the dependency graph, evaluates expressions, and computes the diff between desired and current state. The plan is presented for approval. Apply phase walks the dependency graph in topological order, executing creates, updates, and deletes in parallel where possible. After all operations complete, Terraform writes the final state. If any operation fails, the run stops and partial state is saved.
What is the provider reattach pattern for debugging Terraform providers?
Provider reattach is a debugging technique where you start a provider binary in debug mode and then configure Terraform to connect to it instead of spawning a new provider process. You set the TFREITTICHPROVIDERS environment variable with a JSON object mapping provider addresses to their debug server addresses. The provider binary, started with the debug flag, prints the reattach configuration to stdout. This allows you to attach a Go debugger, set breakpoints, and inspect provider behavior during real Terraform operations without modifying the provider source code to add logging.
What is the Terraform plan file format?
A Terraform plan file, typically saved with tfplan extension, is a binary encoded file containing the complete plan including prior state, configuration, provider schemas, and planned resource changes. It is not human-readable in its binary form and must be viewed with Terraform show plan file or converted to JSON with Terraform show JSON plan file. The JSON format is the primary format for programmatic consumption. It contains resource changes with before and after values, change actions, create, update, delete, no-op, unknown values for computed attributes, and metadata about the configuration.
What is the resource changes structure in a Terraform plan JSON?
In the Terraform show JSON plan output, resource changes is an array of objects, each representing a plan change to a resource. Each object contains the resource address, provider address, the change action, create, update, delete, replace, no-op, the before values, current state, the after values, plan state with unknown values marked, and a Boolean indicating whether the resource requires replacement. The unknown values are represented as null with an after unknown object, indicating which attributes will be known after apply. This structure enables policy tools and automation to inspect every plan change programmatically.
What are Terraform stacks?
Terraform stacks is a newer feature in HCP Terraform that introduces a higher-level abstraction above workspaces for orchestrating complex multi-component infrastructure deployments. A stack is defined by tfstack.hcl configuration files that compose multiple components, where each component is backed by a Terraform configuration that manages a subset of the infrastructure. Stacks support a deployments layer that defines multiple named deployments of a stack with different variable values, enabling a single stack definition to be deployed to dev, staging, and production environments with appropriate configuration for each.
What is a component block in Terraform stacks?
A component block in a Terraform stacks configuration defines a unit of infrastructure managed by a Terraform module. Each component specifies the source module, any input variables, and the providers it requires. Components within a stack can reference each other's outputs, creating dependencies similar to module composition in regular Terraform. Components are the building blocks of a stack, analogous to a workspace in traditional Terraform. They are provisioned and destroyed as a unit, but can be parallelized when they have no dependencies, enabling efficient multi-component infrastructure deployments.
What is a deployment block in Terraform stacks?
A deployment block in a Terraform stacks. tfdeploy.hcl file defines a specific named deployment of a stack with particular variable values and identity configuration. You might have dev, staging, and production deployment blocks, each providing environment-specific values to the stack's components. Deployments enable the Heroku-style model, where the same infrastructure definition is promoted across environments by applying the same stack configuration with different variable values, providing consistency while allowing environment-specific customization through deployment-level variables and identity tokens.
What are ephemeral values in Terraform?
Ephemeral values are values that exist only during a Terraform run and are never persisted to state or plan files. They are generated by ephemeral resources and provider-defined functions that return ephemeral results. Ephemeral values can be passed to resource configurations for authentication or one-time bootstrap purposes, but cannot be stored in resource state. Any attribute that receives an ephemeral value must itself be declared ephemeral in the schema, forming a chain of ephemeral safe attributes. This guarantees that short-lived credentials and tokens never appear in Terraform state, addressing one of the primary security concerns with Terraform secret management.
What are write-only attributes in Terraform?
Write-only attributes, introduced in Terraform 1.11, are resource attributes that can be set in configuration, but are never stored in state or shown in plan output. They are used for sensitive inputs like passwords and secrets that the provider needs during create or update operations, but that should not persist. Unlike sensitive attributes which are stored in state but redacted from display, write-only attributes are genuinely not stored anywhere after the operation completes. This enables true secret hygiene for credentials that providers need only once during resource creation.
What are provider-defined functions in Terraform?
Provider-defined functions, introduced in Terraform 1.8, allow provider developers to expose custom functions that users can call in Terraform expressions, just like built-in functions. These functions are defined in the provider schema and implemented in Go. They receive arguments, perform provider-specific logic, and return values. This enables providers to expose utility functions for their specific domain. For example, an AWS provider function to compute IR and TKS, a Kubernetes provider function to generate resource names, or a Vault provider function to generate dynamic secret values without requiring external data sources.
What is state file encryption in Terraform?
State file encryption protects the Terraform state at rest by encrypting the state file contents before writing them to the backend. OpenTofu 1.7 introduced native state encryption with configurable key providers including AWS KMS, GCP KMS, Azure Key Vault, OpenPGP, and PBKD F2. HashiCorp Terraform relies on backend-level encryption, for example, S3 server-side encryption or Terraform Cloud's built-in encryption. In Terraform Enterprise, all state is encrypted at rest using an internal encryption key. True end-to-end encryption, where the plaintext state never leaves the client, requires client-side encryption before writing to the backend.
What is the bootstrapping problem in Terraform?
The bootstrapping problem refers to the circular dependency between Terraform configurations and their own backends. You cannot use Terraform to create the S3 bucket and DynamoDB table that your Terraform state will be stored in, because that state itself needs to be stored somewhere before those resources exist. The conventional solution is to use a separate bootstrap configuration with a local backend to create the backend infrastructure. Then migrate the local state to the newly created remote backend. Another approach uses external scripts or CloudFormation/IRM templates to pre-create the state backend infrastructure.
What is the chicken and egg problem with Terraform state backends?
The chicken and egg problem describes the situation where creating the infrastructure for your Terraform remote backend requires running Terraform, but running Terraform requires the backend to exist. For AWS, this means creating the S3 bucket and DynamoDB table before Terraform can use them as a backend. Common solutions include using a separate minimal Terraform configuration with a local backend to bootstrap the backend resources. using a WSCLI scripts or CDK to create the backend infrastructure, or using Terraform Cloud, which eliminates the bootstrap problem by providing a managed backend immediately.
What is the God module anti-pattern in Terraform?
The God module anti-pattern occurs when a single Terraform module manages an excessively broad scope of resources, an entire application stack, all environments, or all cloud account resources in one configuration. God modules become slow to plan and apply, are risky to change because any modification touches the entire infrastructure, makes state management difficult, prevent teams from working independently, and cannot be reused. The solution is to decompose large configurations into focused modules with clear boundaries, each managing a specific layer or component, and compose them at the root level with explicit interfaces.
What is secret sprawl in Terraform?
Secret sprawl in Terraform refers to the uncontrolled proliferation of sensitive values across Terraform configurations and state files. Secrets may be hard-coded in TF files, stored in TF-vars files committed to version control, or embedded in plaintext in state files. Over time, secrets spread across many configurations and become impossible to rotate or audit. Addressing secret sprawl involves using external secret management systems like Vault or a WS Secrets manager as data sources, marking sensitive variables and outputs appropriately, encrypting state at rest, and never committing secret values to version control.
What are the anti-patterns in Terraform module design?
Common Terraform module anti-patterns include overgeneralization, creating modules with dozens of optional variables that are complex to use and test. Undermodularization creates monolithic root modules with hundreds of resources. Exposing all resource attributes through module variables creates brittle interfaces that change frequently. Creating modules for single resources adds indirection without value. Using count for resources that should use for each causes unnecessary replacements. Hard-coding environment-specific values inside modules prevents reuse. Circular module references create dependency cycles that Terraform cannot resolve. Well-designed modules have narrow, stable interfaces and encapsulate sensible defaults.
What is the factory pattern in Terraform?
The factory pattern in Terraform creates many instances of the same type of resource from a single data-driven configuration, where the collection of resources to create is defined in a data structure, often a map of objects in a TF-vars file or fetched from a data source, rather than in code. For example, a security group's factory reads a map of group definitions and creates each group with its rules using for each. This pattern is highly scalable and separates the what to create from the how to create it, making it easy to add or remove resources by editing the data structure rather than the Terraform code.
What is blue-green infrastructure deployment with Terraform?
Blue-green deployment with Terraform maintains two identical infrastructure environments, blue, current active, and green, new version, and switches traffic between them. Terraform manages both environments and a traffic routing resource, like a load balancer or DNS-weighted routing. The workflow deploys new version to the inactive environment, runs health checks, then updates the routing resource to point to the new environment. Terraform's create before destroy lifecycle setting and weighted routing resources can atomically switch traffic. Modules parameterized by color enable reusing the same configuration for both environments.
What is immutable infrastructure with Terraform?
Immutable infrastructure is the principle that servers and infrastructure components are never modified after creation. Instead, they are replaced with new instances. Terraform enforces immutability by triggering resource replacement when configuration changes rather than in-place modification. Combined with tools like Packer for building golden IMIs, immutable infrastructure with Terraform means no configuration drift because every change results in a clean replacement resource. This approach improves reliability, security, and reproducibility at the cost of requiring robust deployment processes that handle traffic draining and state migration during replacements.
What is the Strangler Fig pattern with Terraform?
The Strangler Fig pattern is a migration strategy for incrementally refactoring existing infrastructure under Terraform management. Rather than performing a risky Big Bang migration, you import existing resources into Terraform one component at a time while maintaining the legacy infrastructure alongside. New infrastructure is built using Terraform, while old infrastructure is progressively migrated or decommissioned. This pattern reduces migration risk and allows teams to gain Terraform experience on less critical systems before tackling production-critical infrastructure. Moved blocks and the removed block are important tools in this migration process.
What is GitOps with Terraform?
GitOps with Terraform treats the Git repository as the source of truth for infrastructure state, using pull request workflows and automated CD pipelines to apply infrastructure changes. Every change to Terraform configuration goes through a pull request where the plan output is automatically posted as a comment. After review and approval, merging the PR triggers an automated apply. Tools like Atlantis, Terraform Cloud with VCS integration, or custom CI pipelines implement this workflow. GitOps with Terraform provides audit trail through Git history, peer review for infrastructure changes, and automated enforcement of CI checks like formatting, validation, and policy evaluation.
What is Terraform Enterprise?
Terraform Enterprise, TFE, is the self-hosted version of Terraform Cloud that organizations deploy in their own data centers or private cloud environments. It provides all the features of Terraform Cloud, including remote execution, private module registry, Sentinel policies, team management, SSO, and audit logging, but runs on infrastructure you control. TFE is used by organizations with strict data residency requirements, air-gapped environments, or compliance mandates that prevent using external SaaS services. It requires operational expertise to maintain the application, database, and supporting infrastructure.
What is HCP Terraform?
HCP Terraform is the current name for the managed service previously known as Terraform Cloud. HCP stands for HashiCorp Cloud Platform, which is the unified cloud platform for HashiCorp products. HCP Terraform offers free, plus, and business tiers with progressively more features including Sentinel policies, audit logging, SSO, run tasks, and private agents. The rebranding to HCP Terraform reflects tighter integration with other HCP services like HCP Vault, HCP Console, and HCP Waypoint as part of HashiCorp's platform strategy. The IPI and feature set remain compatible with the Terraform Cloud name.
What are audit log streams in Terraform Cloud?
Audit log streams in Terraform Cloud enable forwarding audit events to external log management systems like Splunk, Datadog, or custom HTTPS endpoints in real time. Audit events include workspace creation and deletion, run starts and completions, variable changes, team permission modifications, policy evaluations, and user authentication events. Streaming audit logs enables security information and event management workflows, compliance reporting, and security monitoring for all Terraform operations. This feature is available in the Terraform Cloud Business tier and Terraform Enterprise.
What are Terraform Cloud team permissions?
Terraform Cloud teams are groups of users with shared permissions assigned to workspaces, projects, or at the organization level. Workspace-level permissions include read, plan, write, and admin access. Plan permission allows viewing and creating runs but not applying. Write permission enables applying approved plans. Organization-level permissions control access to the private module registry, policy management, workspace creation, and organization settings. Teams enable organizations to implement least privilege access at fine granularity, ensuring operators can only access and modify the workspaces relevant to their responsibilities.
What is SSO configuration in Terraform Cloud?
Terraform Cloud supports SSO, single sign-on. Integration with SML 2.0 compliant identity providers like Okta, Azure ID, Google Workspace, and others. With SSO enabled, users authenticate through the organization's identity provider rather than with HashiCorp credentials. Team membership can be managed through IDP group mappings, automatically assigning Terraform Cloud team memberships based on IDP group membership. SSO is available in the business tier and enables centralized identity management, MFI enforcement through the IDP, and automated user provisioning and deprovisioning.
What is the no-code module feature in Terraform Cloud?
No-code modules in Terraform Cloud allow platform teams to publish modules that end users can deploy through a UI wizard without writing any HCL code. Module inputs are presented as form fields, and deploying creates a Terraform Cloud workspace with the module configured. This enables self-service infrastructure provisioning where developers request standard infrastructure, databases, queues, caches, via a catalog, without learning Terraform syntax. No-code modules enforce organizational standards by limiting what configuration is exposed to end users while hiding the underlying infrastructure complexity behind a controlled interface.
What is the Terraform test mocking framework?
The Terraform test framework supports mock provider and mock resource blocks in tf-test-hcl files that substitute real provider implementations with simulated ones during testing. Mock providers return configurable attribute values for resources and data sources without making any API calls. You can define override data, override resource, and override module blocks to control exactly what attribute values are returned. This enables unit testing module logic, variable validation, output computation, conditional resources, quickly without credentials or cloud infrastructure, making tests run in seconds rather than minutes.
What is the run block in Terraform test?
A run block in a tf-test-hcl test file executes one Terraform operation as part of a test sequence. Each run block can specify a plan or apply command, provide variables, select a module to test, and contain assert blocks that check conditions after the run completes. Multiple run blocks in a test file execute sequentially using the same state, enabling multi-step test scenarios. For example, create a resource, verify its state, make a configuration change. Verify the planned update, apply it, and verify the final state. The testing framework cleans up all real resources after the test file completes.
What is the assert block in Terraform test?
An assert block inside a run block in a test file specifies a condition and an error message. The condition is a Terraform expression that must evaluate to true for the test to pass. If the condition is false, the test fails with the specified error message. Assert conditions can reference resource attributes, module outputs, and data source attributes from the current test run state. Multiple assert blocks can appear in a single run block, each checking different invariants. Well-written assert conditions check specific expected values rather than just checking for non-null to be meaningful.
What is expect failures in Terraform test?
The expect failures argument in a run block specifies a list of resource, data source, check block, or input variable addresses that are expected to fail during the test run. This enables negative testing, verifying that invalid configurations are correctly rejected. For example, you can test that a variable validation rule raises an error for an invalid value by providing the invalid value and listing the variable in expect failures. If the expected failure does not occur, the test fails. This enables comprehensive testing of error conditions and validation rules within the test framework.
What is the concept of configuration drift, and how does Terraform handle it?
Configuration drift is the gradual divergence of actual infrastructure state from the desired state defined in configuration, typically caused by manual emergency changes, automated systems, or external processes modifying resources outside Terraform. Terraform detects drift during the refresh phase of Terraform plan by querying the current state of each resource from the provider IPI and comparing it against the recorded state. Drift appears in the plan as unexpected changes. Terraform can reconcile drift by applying the configuration to restore desired state, or you can acknowledge intentional drift by running Terraform apply refresh only to update state.
What is state file size management in Terraform?
Large Terraform state files with thousands of resources can cause performance problems, slow plans, long lock hold times, and large state diffs. Strategies for managing state size include splitting monolithic configurations into multiple smaller configurations, each with their own state, using module boundaries as natural split points. Archiving resources no longer managed by Terraform using the removed block, and using targeted applies with target during development to work on specific resource subsets. Some organizations limit single-state files to a few hundred resources as a rule of thumb, with cross-state references via Terraform remote state or external data sources.
What are provider network mirroring and file system mirroring?
Provider network mirroring configures Terraform to download providers from an internal mirror server that implements the provider network mirror protocol instead of the public Terraform registry. This is used in enterprises where all software must be sourced from internal artifact stores. File system mirroring uses a local directory tree populated by Terraform provider's mirror command to serve providers without network access. Both approaches require configuring the provider installation block in /Terraform RC or Terraform-CLICONFIGFILE. Network mirrors require implementing the registry protocol. File system mirrors work offline but must be pre-populated and kept up to date.
What is the resource lifecycle during a Terraform destroy?
During Terraform destroy, Terraform builds the inverse dependency graph. Resources are destroyed in reverse dependency order, so that dependent resources are destroyed before the resources they depend on. For example, EC2 instances are destroyed before security groups, and security groups before the VPC. The destroy plan shows all resources with delete actions and requires confirmation. With prevent destroy set to true, destroy is blocked with an error. Custom destroy time provisioners run just before the resource is destroyed, enabling cleanup actions. After all destroys complete, state is updated to reflect the empty infrastructure.
What is a Terraform workspace in the context of Terraform Cloud architecture?
In Terraform Cloud, a workspace is the fundamental unit of infrastructure management that encapsulates a set of configuration, state, variables, and run history. Each workspace tracks a single Terraform root module and has its own remote state, execution environment, team permissions, and policy evaluation context. Workspaces can be organized into projects for logical grouping and access management. The workspace concept maps to a single environment or deployment of a particular infrastructure component. Large organizations may manage hundreds or thousands of workspaces, requiring programmatic management via the Terraform Cloud API or providers.
What is the workspace resource in the Terraform Cloud provider?
The TFE workspace resource in the Terraform Cloud/Enterprise provider allows managing Terraform Cloud workspaces as Terraform infrastructure, using Terraform to manage Terraform. This enables creating, configuring, and deleting workspaces programmatically, setting workspace variables, configuring VCS integration, assigning teams, and setting execution mode. This meta-Terraform pattern allows platform teams to provision new workspaces for application teams in a self-service manner through a separate workspace management Terraform configuration. Applying organizational standards consistently across all managed workspaces.
What are deferred actions in Terraform?
Deferred actions are a Terraform plugin framework feature that allows providers to signal that a resources plan cannot be completed in the current plan because certain information is not yet available. When a provider defers an action, Terraform marks the resource as having an unknown plan result and continues planning other resources. On subsequent applies, after the necessary information becomes available, the deferred resources are planned and applied. This enables scenarios where a resource depends on values that can only be determined at apply time without causing hard plan failures, improving the user experience for complex dependency chains.
What is Terraform's graph walk algorithm?
Terraform's graph walk algorithm traverses the resource dependency graph using a topological sort combined with concurrent execution of independent nodes. The graph is a directed acyclic graph, DIG, where edges represent dependencies. Terraform processes nodes with no remaining unresolved dependencies first, executing up to the parallelism limit concurrently. As nodes complete, they unblock their dependents, which are then queued for execution. For destroy operations, the edges are reversed, so dependents are processed before their dependencies. This algorithm ensures correct ordering while maximizing parallelism, resulting in fast apply times for large infrastructure graphs.
What is provider version lock, and how do you manage it across teams?
Provider version locking is managed through the Terraform lock HCL file committed to version control, which ensures all team members and CI systems use identical provider versions. Managing provider upgrades requires a deliberate process. A team member runs Terraform init upgrade to select new provider versions within the configured constraints, reviews the updated lock file, tests the upgrade, and submits a pull request. The PR can be automatically validated by running Terraform plan against the test environment. For organizations running many Terraform configurations, automated tools like RenovateBot or Dependabot can create provider upgrade PR tickets automatically.
What is the TICOS, Terraform Automation and Collaboration Software, ecosystem?
TICOS refers to the ecosystem of tools built around Terraform that provide automation, collaboration, governance, and enterprise features. Beyond HashiCorp's own Terraform Cloud and Enterprise, the ecosystem includes Atlantis, open-source PR automation, Spacelift, advanced Git ops with policy, Env0, collaborative Git ops with cost, Scalar, multi-tenant Terraform management, and Digger, open-source lightweight automation. TICOS tools provide features like run policies, drift detection, audit logging, cost management, and multi-cloud support on top of the core Terraform plan and apply workflow. Organizations choose TICOS tools based on scale, compliance requirements, and team preferences.
What is Spacelift?
Spacelift is a commercial Terraform automation and collaboration platform that extends beyond Terraform Cloud's capabilities with support for multiple IIC tools: Terraform, OpenTofu, Pulumi. CloudFormation, Ansible, and Kubernetes. It provides policy as code with OPA, advanced GitOps workflows, stack dependencies for orchestrated multi-stack pipelines, drift detection, Terraform state management, and a worker pool for private network execution. Spacelift's stack concept is similar to Terraform Cloud workspaces, but integrates tighter GitOps workflows and cross-dual orchestration, making it popular in organizations using multiple IIC tools alongside Terraform.
What is Env0?
Env0 is a cloud-based Terraform collaboration platform focused on cost management and self-service environments. It provides workflow automation, budget controls, automatic environment TTL that destroy environments after a set time, cost monitoring per workspace, and drift detection. Env0 self-service features allow developers to provision environments from pre-approved templates without direct Terraform knowledge. Its cost controls and environment scheduling features are particularly valuable for managing ephemeral development and testing environments, where cost optimization is important. Env0 supports Terraform, Terragrunt, Pulumi, and other IIC tools.
What is the recommended module structure for a publishable Terraform module?
A publishable Terraform module follows the standard registry module structure, with a main TF containing primary resources, variables TF defining all input variables with descriptions and type constraints, outputs TF defining all output values with descriptions, versions TF or required providers in main TF specifying provider requirements, and a REIDM-EMD with usage documentation. Submodules live in modules/subdirectory. Examples live in examples/subdirectory showing common usage patterns with working configurations. A CHINGELOGMD tracks version history. Modules are versioned using semantic Git tags. This structure enables automatic documentation generation and fulfills Terraform registry requirements for module publication.
What is the recommended approach for secrets management in Terraform?
The recommended approach for secrets management avoids storing sensitive values in Terraform state entirely. Use ephemeral resources, Terraform 1.10+. For short-lived credentials from systems like Vault, use write-only attributes, Terraform 1.11+. For passwords required during resource creation, store sensitive configuration in dedicated secrets managers, AWS Secrets Manager, HashiCorp Vault, Azure Key Vault, and reference them via data sources only when needed. Never storing them as Terraform variables. Use OIDC dynamic credentials for cloud provider authentication. Enable backend state encryption. Never commit TFVARs files containing secrets. Audit state files regularly for accidentally stored sensitive values.
What is a Terraform module registry source address?
A module registry source address uniquely identifies a module in a registry with the format hostname/namespace/module/provider, where hostname is optional and defaults to registry Terraform.io. For example, registry Terraform.io/HashiCorp/console/Oz references the console module for a WS in HashiCorp's namespace. Private registry modules in Terraform Cloud use the address appterraformio/organization/module/provider. The version constraint is specified separately in the module block. Git sources use the git double-colon prefix with a URL and an optional ref query parameter for a specific tag or commit. Local modules use relative paths starting with / or /.
What is a Terraform workspace variable versus a workspace environment variable?
In Terraform Cloud workspaces, there are two types of variables. Terraform variables are passed to the Terraform configuration as input variables and appear in the Terraform plan context, equivalent to var flags. Environment variables are set as OS environment variables in the execution environment and can be used for provider authentication credentials, TFVIR prefixed variables, and Terraform runtime settings. Sensitive variables of either type are stored encrypted and not displayable after setting. Environment variables prefixed with TFVIR are automatically converted to Terraform input variables at runtime, while provider credentials are usually raw environment variables like OSXSKey ID.
What is the life cycle of a Terraform Cloud run?
A Terraform Cloud run progresses through several phases. Pending means the run is queued waiting for a previous run to complete. Planning phase runs Terraform plan and posts the output. Cost estimation calculates monthly cost impact if enabled. Policy check evaluates Sentinel and OP policies against the plan. Awaiting confirmation pauses for human approval if require approval is configured. Applying phase runs Terraform apply. Post-apply policy checks run if configured as post-apply. Completed or errored terminates the run. Each phase produces logs, and the overall run result is available via webhooks and notifications for CI/CD integration.
What is Terraform's treatment of unknown values during planning?
Unknown values, represented as known after apply. In plan output are resource attributes that are computed by the provider during apply and cannot be predicted during planning. They arise when a resource ID, auto-generated name, or other provider-assigned attribute is referenced in another resource's configuration. Terraform propagates unknowns through the dependency graph. If an argument to resource B depends on an unknown attribute of resource A, resource BTKS plan also shows unknown values. Expressions that depend entirely on unknown values are evaluated to unknown. Resources using for-each cannot have an unknown set, which is why for-each values must be fully known at plan time.
What is the purpose of the Terraform TF state backup file?
Terraform automatically creates a backup of the previous state file named Terraform TF state backup before writing a new state during apply. This provides a one-step rollback option if an operation corrupts or unintentionally modifies state. With remote backends, this backup behavior is not relevant because backend operations are transactional and versioned by the backend. For local backends in development environments, the backup file provides a safety net. When using the local backend in CI or production, state versioning is not provided, which is one of many reasons remote backends are strongly recommended for production use.
How do you implement a break glass procedure with Terraform?
A break glass procedure for Terraform provides emergency access to apply critical changes outside the normal workflow when the CI/CD pipeline is broken or unavailable. It involves maintaining a documented procedure for authorized operators to run Terraform locally against production state using short-lived emergency credentials. Key elements include using separate emergency IAM roles with time-bounded access, requiring MFI logging all commands, committing any emergency changes immediately after applying to maintain Git as the source of truth, and post-incident review to prevent recurrence. Break glass access should be audited via CloudTrail or equivalent audit logs and used extremely rarely.
What is Terraform's approach to null values?
Null in Terraform represents the absence of a value and behaves differently from empty strings or zero values. When a resource attribute is set to null, it is treated as if the attribute was not set at all, allowing the provider to use its default value. Null is the value of optional attributes not specified in configuration. Expressions like try return null when all alternatives fail. Legacy optional. Type constraints in module variables allow callers to omit values that default to null. The coalesce list and coalesce functions handle null by skipping null values. Null values are not stored in state for optional computed attributes.
What is the difference between Terraform Plan and Terraform Plan Out?
Terraform Plan without out generates and displays the plan but does not save it. So the next Terraform apply generates a fresh plan that might differ if infrastructure changed between plan and apply. Terraform Plan Out equals plantf plan saves the exact plan to a binary file. And Terraform Apply plantf plan executes that exact plan without generating a new one. Using saved plan files in CI provides a two-phase pipeline where the plan is reviewed, and the exact same plan that was reviewed is what gets applied. Preventing the TOC/TOU vulnerability, where infrastructure changes between plan review and apply execution. Saved plans expire if providers or configurations change.
What is resource targeting, and when should you avoid it?
Resource targeting with target limits plan and apply to specific resources, which can create inconsistency between state and configuration when targeted resources have dependencies on untargeted ones. Terraform warns that targeting is for exceptional use cases only. Acceptable uses include emergency recovery from partial failures, iterative development when testing a specific new resource, and initial bootstrapping when dependency cycles prevent a full apply. Avoid target in normal CI/CD pipelines for production changes without emergency justification or as a workaround for inadequate module design. If you find yourself using target regularly, it signals architectural problems in the configuration that should be addressed.
What is dynamic credentials, and how does it improve security posture?
Dynamic credentials in the context of Terraform Cloud means using short-lived, automatically generated credentials for cloud provider access rather than static long-lived access keys. Implemented via OIDC trust relationships. Each Terraform Cloud run generates a unique JWT token that is exchanged for temporary cloud credentials valid only for the duration of the run. This eliminates credential rotation requirements, reduces the blast radius of any credential exposure, provides per-run audit trails in cloud provider access logs, and removes the sensitive credential management burden from platform teams. It is the security best practice for all Terraform Cloud workspaces connecting to AWS, Azure, or GCP.
What is the provider installation configuration in Terraform?
The provider installation configuration in the CLI configuration file /terraformrc or terraformrc controls how Terraform discovers and downloads providers. The provider installation block can chain multiple installation methods with fallback behavior. File system mirror specifies local directories containing provider binaries. Network mirror specifies an HTTPS server implementing the mirror protocol. Direct allows downloading from the registry for providers not found in mirrors. You can exclude specific providers from direct download with an exclusion list, ensuring all providers come from controlled internal sources in regulated environments. This configuration is essential for air-gapped and enterprise environments.